This is Babitha, working as Assistant Professor in the Department of ECE in Institute of Aeronautical Engineering. In this session, we are going to discuss the questions related to the operational amplifier, that is the fifth module. So, in the questions, we are having three types, that is part A belongs to the problem solving and critical thinking questions, and part B belongs to the long answer questions, and part C belongs to the short answer questions. So, while moving to the problem solving and critical thinking questions, here the first problem related to the operational amplifier here. So, here for the op-amp, the given slew rate value as 0.5 microseconds for 0.5 volts per microseconds. Slew rate is given 0.5 volts per microseconds. Used an inverting amplifier to obtain a gain of 100, and the voltage gain versus frequency characteristics of the amplifier up to flat till frequency 10 kHz. Determine the maximum peak to peak input signal, that is P peak to peak, can be applied without any distortion to the output. The maximum frequency of the input signal to obtain the sine wave of 2 volts peak. So we have to find the peak to peak voltage as well as the frequency, how much we required here. So this problem we have already discussed in the problems and operational amplifier session. So we need to find the peak to peak voltage from the given value as well as the maximum frequency required for the operational amplifier. And next, the next problem related to integrator circuit. Design integrator to integrate an input signal that varies frequency from 10 Hz to 1 kHz here. So the frequency value is 10 Hz to 1 kHz. If a sine wave of 1 volt, so the input signal value is 1 volt. Peak, the frequency value is 1000 Hz, is applied to this differentiator, draw the output waveform. So here for the integrator circuit, the output voltage we have to take it as minus 1 by RFC integration of V naught of t dt we have to take here, V naught of t equal to. So after substituting the given values here, we will get the output voltage. So here they given the signal as the input signal. The input signal is the sinusoidal signal, so we have to take the sinusoidal signal like this. Okay, this is the VA. So the corresponding the output voltage, we will get it as the cosinusoidal signal for the given sinusoidal signal. So this is the output voltage. So in this way, we have to calculate the values here. This problem we have already discussed in the problems on the op-amp integrator circuits. And next, problem related to the differentiator circuit. So the differentiator will differentiate the input signal varies a frequency from 10 Hz to 1 kHz. So if a sine wave of 1 volt peak, so the input signal value is 1 volt peak to peak. 1 volt peak we are applying with a frequency of 1000 Hz. Apply the differentiator, draw the output waveform here. So in the case of differentiator, the output voltage is minus RF C1 into differentiation of input voltage Vi here. So from this, we have to find the output signal, and the input signal, they given it as the sinusoidal signal. And after differentiation, what is the output signal we are going to get? We need to calculate here. The cosinusoid signal again we will get from the differentiator. So each and every step we have to explain and derive clearly here. And this problem we have already discussed in the problems on op-amp differentiator session. And next, to design and draw the waveforms of 1 kHz square wave generator using 555 timer for duty cycle of 25% and 50%. So here we have to draw the square wave generator by utilizing the op-amp circuit by providing the positive feedback as well as the negative feedback. Okay, and after drawing that, we have to find the duty cycle of that particular square wave generator here. And next, explain about the term common mode rejection ratio input offset voltage, input offset current, input bias current, and output offset voltage with respect to the operational amplifier. Here input offset voltage is nothing but whenever both the inputs of the operational amplifier are 0, the output voltage must be 0 here. But in this condition, the practical op-amp shows a small non-zero voltage here. So in order to minimize, this is due to the mismatching present in the internal circuit of the operational amplifier. So that input offset voltage will cause error in the practical applications for the op-amp used. So to make such voltage as 0, it is necessary to apply some amount of small difference voltage between the two input terminals of the operational amplifier. So that voltage we are calling it as the input offset voltage here. So this we are indicating here it as the input offset voltage, that is the difference of the VDC1 minus VDC2 here. In the practical amplifiers, the value of this one will be there, but in the ideal operational amplifier, almost the input offset voltage is 0 here. And next, input offset current. So that is the input offset current is the algebraic difference between the currents into the inverting terminal and the non-inverting terminal of a balanced amplifier. That is the difference of current which is flowing in the inverting terminal and the current which is flowing in the non-inverting terminal. So for the practical operational amplifier, the value of this one is 200 nanoamperes. But in the ideal case, this value is 0. So while coming to the input bias current. So input bias current is the average of the current entering into the input terminals of balanced amplifier, and it is denoted as IB here. So this one will be denoted here as IOS, and this one will represent with IB, that is the average of both the currents which are entering into the two input terminals of the operational amplifier. So practically this value is 500 nanoamperes. In the ideal operational amplifier, this value is 0. And next, output offset voltage. So the voltage present in the output of the op-amp when its differential input voltage is 0 is called the output offset voltage. And next one is CMRB. Common mode rejection ratio is nothing but it is the ratio of common mode gain to the differential mode gain here. So that one will give the common mode rejection ratio of the operational amplifier. So in the ideal operational amplifier, this value is infinity, but in the practical case, the value will be large. And next, we are coming to the next problem. Design an op-amp differentiator that will differentiate an input signal with f maximum of 100 Hz here. So in order to design the differentiator circuit, here we need to find the resistances R1, RF, C1, and for the practical differentiator in the feedback again we will add one more resistance here, that is R1 resistance. So here we are having the C1 RF resistances, and the feedback again we will add the R1 resistance. So here we have to draw the circuit in this way. In the feedback we are having the resistance and the one more resistor here. So positive, negative, here we will apply the input signal, here we will get the output signal. So in this way we have to draw the circuit and we have to find the frequency, find the signal with the frequency of f equal to 100 Hz. So this one we discussed already in the problems on the differentiator, op-amp differentiator session. And next, for a non-inverting single supply AC amplifier with input resistance is 50, input capacitance is 0.1 microfarads, and the C1 is 0.1 microfarads, and all the three resistances given as 100 kilo ohms, and the feedback resistance is 1 mega ohm, and the supply voltage given it is plus 12 volts. Here determine the bandwidth as well as voltage swing of the amplifier. So this problem we have already discussed on the problems on op-amp session here. Just we have the formulas, substitute the given values in that formula. And next explain the common mode gain and differential gain of a differential amplifier. So here common mode gain is nothing but the AC here, differential gain is nothing but the AD here. So here V0 by common mode signal output voltage by common mode voltage, and here it is output voltage by differential voltage here. So these are the two gains which we can expect in the case of differential amplifier. Here the input signal is not equal to the first input signal is not equal to the second input signal, but here the input signal is equal to the second input signal. So that's why we are calling it as the common mode gain, and this one is the differential gain here. So always the differential gain is high compared to the common mode gain. Design and draw square waveforms of 1 kHz square waveform generator using 555 timer with a duty cycle of 25% and 50%. So this is the problem we have already discussed in the previous slides, and this problem we have also discussed in the problems on the operational amplifier or waveform generators using operational amplifier. And next, design an op-amp integrator that will integrate input signal with the F minimum of 100 Hz. So here we have to design the integrator circuit. Before going to that, we have to find all the required components for the practical integrator. So after finding the values, we have to draw the practical integrator circuit, and we have to draw the input output waveforms with a frequency of 100 Hz. And while coming to the next part, that is long answer questions. So first one is explain the following terms in an operational amplifier. It is input bias current, input offset voltage, and current, and slew rate. So input bias current is nothing but the average of the current entering into the input terminals of the balanced amplifier, and it is denoted as IB. So we are indicating with the IB. So it is the average of the current which is entering into the inverting terminal as well as non-inverting terminal here. So ideally this value is 0, but in the practical operational amplifier this value is 500 nanoamperes. And next, input offset voltage. So generally whenever both the input voltages are 0, the output voltage must be 0 in the case of operational amplifier. But in the practical case, we are getting, instead of 0, we are getting some practical output voltage here. So in order to nullify that voltage, we are applying some small differential voltage between the two terminals of the operational amplifier to make the output as 0. So that voltage we are calling it as the input offset voltage here. So input offset voltage we will represent with the VIOS, that is the difference of two voltages for the inverting and non-inverting terminals of the operational amplifier here. And next, slew rate. The slew rate of an amplifier will give the rate of change in the output with respect to time here. So generally we will specify it in volts per microseconds, and we can also write it as variation of output voltage with the variation of the time, that is equal to I by C here. So slew rate indicates how fast the output changes if input is also changing here. So it is specified by the operational amplifier in unity gain conditions here. So slew rate is high means the speed of the system will be high here. And next, explain the operation of non-inverting op-amp and derive the expression for output voltage. So when we can say the particular operational amplifier is non-inverting operational amplifier, means the input signal we will apply to the non-inverting terminal of the operational amplifier here, and we are providing the feedback from the output to the inverting terminal, and this is the compensation resistance RG here. So in the case of non-inverting operational amplifier, output is in phase with the input signal, so that's why there is no negative sign in the output voltage. So the output voltage, if we calculate, we will get it as 1 plus RF by RG into Vin. So the gain value is 1 plus RF by RG here. So how we calculated that value is, we are taking this particular circuit to find the gain value here. So here across VA, the value of voltage is Vn. At VB, the value of voltage is opposite resistance RG by total resistance is RG plus RF into output voltage here. So if we simplify it, we will get the gain value as 1 plus RF by RG here. So that is the gain of the non-inverting operational amplifier. So each and every step we need to explain clearly here, and the operation of the non-inverting amplifier and the circuit of the non-inverting amplifier we need to explain clearly. And next, with the neat diagram, explain about square wave generator and derive the frequency of oscillation. So square wave generator is used to generate the square waves. If we want to design the OPAMPS square wave generator, we are going to utilize both the positive feedback as well as negative feedback in the designing of the uh, square wave circuit utilizing 741 operational amplifier. So in this case, initially capacitor is in uncharged condition and no voltage is applied between two terminals, but because of some input bias voltage present across the positive terminal, so the output will reach to the positive saturation level. So through this output voltage and through resistance R1, the capacitor will charge to the voltage VC. So once this VC voltage is higher than this voltage, now the output becomes minus V saturation. So once it is negative, means the capacitor will discharge through this resistance R1 again. So this voltage is high again. So it will again shift to plus V sat. So always it is moving from plus V sat to minus V sat because of the charging and discharging of the capacitance. So this is the explanation related to the circuit, and this is the operation, and this is the signal we are getting from the square wave generator, and this one is the capacitor voltage, the charging and discharging of the capacitor, and this is the output voltage. So in order to find the frequency of oscillation, we have to take the upper threshold voltage as well as lower threshold voltage by superimposing the capacitor voltage on the output voltage of the square wave generator. And then we have to find the frequency of oscillation, that is 1 by 2 RFC ln plus V saturation minus V LT by plus V saturation minus upper threshold voltage here. And next one is with a neat diagram explain about triangular wave generator and derive the frequency of oscillation. So once we know the square wave generator, we can also design the triangular wave generator. The output of the square wave generator, if we apply to the integrator circuit, it will provide the triangular wave circuit. So this is the internal circuit of the triangular wave generator. Here we need to explain the each and every component role here and the operation of this circuit. And this is the output of the triangular wave generator. This is the output of the square wave generator. This is after integration, we will get this particular waveform here. And this is the frequency of the oscillation of the triangular wave generator here. So we need to explain in detail this particular circuit here as it is the Lambda oscillation. And next, draw and explain the operation of an op-amp as an integrator for square wave input. So for the integrator circuit, we are having one resistance and capacitor circuit. So the function of the integrator is to perform the integration of the applied input signal here. And because of this charging and discharging levels and this resistance value, we will get the integration of the applied input signal. So the formula here it is minus 1 by R1 CF integral of 0 to t V of t dt here. So here in this case, they are asked for the we have to analyze this particular circuit to find the output voltage. For that, we are applying the KVL across the input side as well as the output side of the circuit, so that we will get two equations, and we are equating the two equations to find the final output voltage. So this is the final output voltage of the integrator circuit. So here C1 minus 1 by RF C1 is the CF R1 is the time constant of the circuit here. So if we apply the square wave to the integrator, we will get the corresponding triangular wave here. So in this way, we need to explain the operation of the integrator circuit, and we have to draw the circuit, and we need to explain the operation of the circuit in detail, and we have to do the analysis to find the output voltage, and for the corresponding given square wave input, what is the output we are getting, we need to explain. And next one, draw and explain the operation of op-amp as a differentiator for sine wave input. So the only difference between the integrator and differentiator here is the differentiator will perform the differentiation of the applied input signal here instead of integration. So if we interchange the capacitor and resistances of the integrator circuit, we can able to get the op-amp differentiator circuit here. So here we have to explain the operation of this differentiator circuit in detail. Okay, and we have to apply the KVL for the input side as well as the output side here. and we have to equate the two equations so that we will get the output voltage as this much. And here output is 180 degrees phase shift between the input signal. Why? Because we are providing the input signal to the inverting terminal of the operational amplifier, and it is having very small time constant. That is the basic advantage of the differentiator circuit. And if you apply the sine wave to the differentiator circuit, we will get the output as the cosine wave here, with the amplitude is same here. And next, with the knee diagram, explain about a free running oscillator and derive the frequency of oscillations here. So free running oscillator we can design by utilizing the op-amp and resistor capacitor circuits here. So for this question, we have to draw this circuit and explain the operation of that one in clearly. And if you how the signal is generating, that is free running oscillator will generate the square wave signal, we need to explain clearly here. And next, design a differentiator to differentiate an input signal that varies in the frequency from 10 Hz to 1 kHz. So frequency range given it as 10 Hz to 1 kHz here. And if a sine wave of that is input signal value is 1 volt and the frequency of this signal is 1000 Hz is applied to this differentiator, draw the output waveform. So for the from the given parameters, we have to draw the differentiator circuit first, that is with the capacitor and the resistor circuit, that is CRF, compensation resistor. Here we are applying the input signal and here we are taking the output signal. It is the minus, it is the 741 operational amplifier. So this is the circuit here. So if we apply the sine wave as the input for this, the output we will get it as, the output signal we will get it as cosine-sided waveform here. So each and every step we need to explain clearly here. And next, draw the output waveform for a sine wave of 1 volt peak at 100 Hz applied to the differentiator. So this problem is similar to the previous problem. Same procedure we need to repeat to solve this problem. So this problem, the 9th problem and 10th problem, we have already discussed in the problems on op-amp differentiator circuits or session. And next, show the op-amp differentiator that will differentiate an input signal with f maximum of 100 Hz. So this particular problem also related to the op-amp differentiator circuit. Here we have to find the required parameters and we have to draw the op-amp differentiator circuit, and when we apply the different input signal to this particular differentiator, what is the output signal we are getting, we have to explain clearly here. And next, find R1 and RF in the lossy integrator so that the peak gain is 20 dB. So gain value is given it as 20 dB and the omega value is 10,000 radians per second and the capacitance value is 0.01 microfarads here. So from this we need to find the R1 as well as RF values here. So after finding that values, we have to draw the integrator circuit and we have to apply different input signal to that integrator circuit and draw the output waveforms corresponding to that integrator circuit. So each and every step we need to explain clearly here. And next, design an op-amp differentiator that will differentiate an input signal with f maximum of 1000 Hz here. So here also we need to draw the op-amp differentiator circuit with the f maximum of 1000 Hz. So to design this type of differentiator, we need to find the capacitance value first and the RF value. Then we need to draw the circuit of this one. And for the different input signals, how it is providing the response, we need to explain clearly. And next, outline the square wave generator using op-amp to oscillate frequency f0 1 kHz and DC supply voltage of plus or minus 12 volts. So for this case, we have to take the square wave generator using operational amplifier and we need to explain the operation of that circuit clearly, how the capacitor is charging and discharging with the applied voltages and how the output waveform is generating. We need to explain clearly here. And next, draw the output waveform for a sine wave of 2 volts at 1000 Hz is applied to the differentiator circuit. So this is a similar kind of problem. They given input waveform as the sine wave with the frequency and the amplitude. And we have to design the differentiator circuit first. Then we need to apply this input signal to that. And what is the output waveform we are getting? So these and all we need to explain clearly here. And next, design a comparator circuit for input voltage 2 volts peak to peak. Sine wave at 1 kHz. Okay, input voltage value VI is given it as 2 volts peak to peak. And the frequency is given it as 1 kHz. And the reference voltage given it as 500 millivolts. And the resistance value is 100 ohms. And the supply voltage is plus or minus VCC is plus or minus 15 volts. And what is the output waveform we need to draw here? So the function of the comparator is to compare the applied input signal with the reference voltage. And it is also two types, inverting comparator as well as a non-inverting comparator. Depending upon that, we will get outputs as either plus V saturation or minus V saturation. So always we will compare the input voltage with the reference voltage here. So if the input voltage is connected to the inverting terminal, means if Vi is greater than V reference, we will get the negative saturation as the output. If Vi is less than V reference, we will get it as plus saturation as the output. So in this way, we have to explain. We have to draw the comparator circuit with the reference voltage for the one input terminal, input voltage for the other input terminal. So after comparison, we will get the output voltage as positive saturation and negative saturation. So by utilizing the voltage levels, we have to draw the output waveform. So in this way, we need to explain the comparator circuit. And we can design it is in the inverting form as well as in the non-inverting form. So this problem we have already discussed in the problems on square wave generator of operational amplifier session. And next one is, what are the limitations of an ordinary op-amp differentiator? Draw the circuit of practical differentiator that will eliminate these limitations. So here limitations of the normal op-amp differentiator is at high frequency signals. When we apply the high frequency signal, it will become unstable and it will lead to the noise problem because of the reactance of the capacitor here. So in order to overcome that problem, we are adding one capacitor in the feedback and one resistor in the inverting terminal of the operational amplifier to nullify these particular problems here. So in this case, first of all, we have to draw the ideal differentiator circuit and we have to derive the output voltage of that one. Then we have to mention the limitations of that one. So to overcome that limitations, what are the elements we are adding and what is the function of that particular added elements, and then operation of the practical differentiator we need to explain here. And next, for a non-inverting single supply AC amplifier, input resistance is 50 ohms. Here it is. Okay, input resistance given it as 50 ohms. And the input capacitance is given it as 0.1 microfarads. And the C1 capacitance is 0.1 microfarads. And the R1, R2 and R3 resistances are 100 kilo ohms. And the feedback resistance is 1 mega ohm. And the supply voltage is plus 12 volts. So in this case, we need to find the bandwidth as well as voltage swing of the AC amplifier. So this particular problem we have already discussed in the problems on the op-amp session. Try to substitute the given values in the formulas to find the asked parameters in the problem. So we're coming to the short answer questions here. So first question is define a differential amplifier here. So the function of the differential amplifier here is it is the type of the electronic amplifier. It will amplify the difference between two input voltages but suppresses the voltage common to the two inputs here. That is nothing but to design the differential amplifier, we need to take the two similar type of transistors with same collector resistance RC1 and RC2 and same emitter resistance RA1 and RA2. It is applied to minus VEE and this is plus VCC. So here we need to apply V1 here need to apply V2 here. This is the Q1 transistor and Q2 transistor here. So the function of the differential amplifier, it is to what is the two voltages we are applying here. It will take the difference of the two voltages V1 minus V2. So the output we are measuring across the collectors of the transistor. And next, list the characteristics of an ideal operational amplifier. So these are the different characteristics of the ideal operational amplifier. So generally it will provide the infinite voltage gain, that is voltage gain equal to infinity, and it will provide the infinite input resistance, that is input resistance is infinity, and if there is no loading on the preceding stage, at that case it can able to provide the infinite input resistance, and the output resistance are not of this one is 0 in the case of ideal operational amplifier, and whenever the input voltage is 0, the output voltage is also 0 in the case of ideal operational amplifier, and it will provide the infinite bandwidth within the range from 0 to infinity hertz, and it will provide the common mode rejection ratio as infinity here. So infinite slew rate, the slew rate also infinity in the case of ideal operational amplifier. If we take any characteristics of the ideal operational amplifier, we will get it as either exactly 0 value or infinite value. But if we take in the practical values, we may not reach to these ideal conditions. We may get it as either low values or high values here. And we're coming to the next question, that is demonstrate the equivalent circuit of operational amplifier. We have already known that the internal stages of operational amplifier consist of different differential amplifiers here, and so because of that reason in the operational amplifier also we are having two terminals. So the two input terminals we are indicating with the 1 and 2 here. That for the two input terminals we are providing the two input voltages. So the differential voltage across the two terminals we are taking it as the VD here. So across the output side, we are having the differential voltage gain it is providing, and the output resistance are not here. So in the practical case, the values may be large here, but it is provide the infinite input impedance and the zero output impedance in the practical operational amplifier. So the OPAMPS parameters in terms of physical components for the analysis purpose is called the equivalent circuit of an operational amplifier. So this circuit shows the op-amp parameters like input resistance and output resistance and the open loop voltage gain. These are the parameters we are indicating in the equivalent circuit. So this circuit amplifies the applied differential voltage between the two input terminals. So the output voltage is the open loop voltage gain AOL into VD, that is equal to AOL V1 minus V2. So where AOL is nothing but the open loop gain of the operational amplifier, and VD is nothing but the differential voltage, and V1 is nothing but the voltage of inverting terminal, and V2 is the voltage of non-inverting terminals. So this is the explanation of the equivalent circuit of the operational amplifier. So while coming to the next question, list the AC characteristics of operational amplifier. So the characteristics of the operational amplifier are open loop voltage gain, output offset voltage, common mode rejection ratio, as well as slew rate here. So these values are either 0 or infinity in the case of ideal operational amplifier, but these values are low or high in the case of practical operational amplifier. And next, list the properties of differential amplifier. So while coming to the different characteristics of the differential amplifier, the differential voltage gain provided by the differential amplifier is high, and the common mode gain is low. The input impedance is high and the output impedance is low, and it is also providing the high common mode rejection ratio and the high bandwidth, low offset voltages and currents. So these are the basic properties of the differential amplifier. Because of this reason only, in order to design the operational amplifier, we are going to utilize this differential amplifier. And next, to define input bias current. So the input bias current generally we will represent with IB. So that is the average of the currents which are flowing into the inverting terminal as well as non-inverting terminals of the operational amplifier. So that we are indicating with IB plus IB minus by 2 here. So the value of this one is 500 nanoamperes for the practical case. In the ideal case, this value is low. List the specifications of practical op-amp here. So practical op-amp characteristics can be approximated closely to reach the ideal case here. But basically practical op-amp characteristics are a little bit different compared to the ideal op-amp characteristics. So if you take the open loop gain, it is the voltage gain of the op-amp when no feedback is applied. So practically this value is several thousands here. And input impedance, it is finite and typically greater than 1 megaohm. But in the field effect transistors, for the input stage, it can be increased up to several hundred megaohms. And the output impedance, it is typically few hundred ohms in the practical case. With the help of negative feedback, it can be reduced to 1 or 2 ohms here. And while coming to the bandwidth, in the ideal case, bandwidth is infinity, but in the practical case, this value is very small here. So by application of the negative feedback, it can be increased to a desired value. And next, input offset voltage. The input offset voltage must be 0. Ideal case, it is 0, but in the practical case, we are getting some value. Input bias current. For ideal operational amplifier, no current which will flow into the terminals. The practical op-amps to have some input current which are very small, of the order of 10 power minus 6 amp to 10 power minus 14 amperes. So these are the practical characteristics of the practical operational amplifier. And next, show the classification of differential amplifier. So here, depending upon how many number of inputs we are utilizing, and depending upon where the output is measuring across the single collector or across the common point of two collectors, we are dividing the differential amplifiers into 4 types. That is dual input balanced output differential amplifier, and dual input unbalanced output differential amplifier, and single input balanced output differential amplifier, and single input unbalanced output differential amplifiers. And next, interpret the equation for common mode gain as well as CMRR of the operational amplifier. So here common mode, to calculate the common mode gain, we require the first input voltage which is flowing into the non-inverting terminal, and the second voltage I am considering which is flowing into the inverting terminal. So the differential voltage VD equal to V1 minus V2. But to find the common mode gain, we require the common voltage, that is the average of these two voltages. So to find the common mode gain, that is the output voltage V0 is equal to the common mode voltage VC here. So this is the common mode gain here. So to find the CMRR, common mode rejection ratio, we have to take the common mode gain to the differential mode gain here. So how to find the differential mode gain here? So the differential mode gain is the V0 by VD here. So this is the CMRR value here. And next, explain the difference between open loop and closed loop gain of operational amplifier. So if you take one particular operational amplifier with the inverting and non-inverting terminal, we are providing the two voltages V1 and V2 something here, and we are getting the output voltage here. Okay, so the open loop gain of the operational amplifier means whenever we are not providing feedback from output to input. So in this case, the differential voltage is V1 minus V2. So the output voltage is open loop gain times the differential voltage VD here. So open loop gain, the open loop gain equal to V0 by VD here. Okay, and if we take the closed loop gain, so if you take the closed loop gain means we have to take the feedback for the operational amplifier through particular resistance RF. So suppose I am applying the VA here. So this one is grounded. This is the output voltage. Okay. So again, we can also take R1 resistance to apply the input voltage. So in this particular case, the output voltage is ACL, A closed loop times the input voltage or the differential voltage here. So here we will get this value as minus RF by R1 into differential voltage or input voltage. So this is the gain in the closed loop gain. In the case of inverting amplifier, in the case of inverting operational amplifier, the gain is minus RF by R1 into VA. Suppose if we add the feedback to the non-inverting terminal, if we add the feedback to the non-inverting terminal, in that case, we are taking the feedback RF here. So resistance R1 is also here. It is grounded. So V0 will measure here. So in this particular case, the closed loop gain ACL is equal to 1 plus RF by R1. So in this way, we are getting the difference of gain in the open loop as well as in the closed loop gain in the inverting mode as well as in the non-inverting mode. And next, show the ideal values of CMRR and input offset voltage. So in the ideal case, CMRR value is infinity and the input offset voltage VIOS is 0 here. Okay, input offset voltage must be 0. Why? Because input offset voltage is nothing but whenever we are not providing any input voltages for the two input terminals of the operational amplifier. So whenever we are not providing any input means we should not get any output here. So that's why in the ideal case this value is 0. Practically the ideally the common mode rejection ratio is also infinite here. Show the circuit diagram of integrator here. So to draw the integrator circuit for the inverting terminal, we are providing the resistance R1, the feedback, C1 capacitance we are providing. So the output we will get it as minus 1 by R1 C times the integral of the applied input signal. So this is the circuit of the integrator circuit. And next, show the circuit diagram of differentiator. So in the previous slide, if you interchange the resistance and capacitance, then we can able to get the differentiator circuit here. And next, show the circuit diagram of square wave generator. So in the case of square wave generator, we are going to utilize both the positive feedback as well as negative feedback. See, this R1 resistance is providing the negative feedback, this R2 resistance is providing the positive feedback. So the charging and discharging of this capacitance will give the output voltage in this square wave generator. And next, show the circuit diagram of triangular wave generator here. So for the square wave generator, the output of square wave generator will be applied to the input of the triangular wave generator. So on input of the integrator circuit, we can able to get the triangular wave as the output. So the output of this one, generally we will get it as the square wave. So the output of this one, we will get it as the triangular wave here. And next, list the limitations of integrator circuit. So the limitations of the ideal integrator circuit is the bandwidth is very poor here and it is used for only small range of input frequencies. So for DC input, that is for frequencies equal to 0, the reactance of the capacitor is infinite. So because of this, the op-amp will goes into the open loop configuration. That is the limitation of the op-amp ideal integrator circuit. And next, outline the formula for non-inverting amplifier. So for the non-inverting amplifier, if we take in the open loop form, we are providing V1 and V2 here. So V1 value we are grounding here for this. We are not providing any input. For the V2 only we are providing the input. So V0 is equal to open loop gain times the V2 we will get here. So the gain is equal to V0 by V2. Okay. Similarly, if you take in the closed loop form, we will get it as R1 RF resistance, input voltage, this one is grounded, and this is the output voltage. So in this case, the output voltage is ACL times the input voltage. So the ACL value is 1 plus RF by R1 into, sorry, input 1 plus RF by R1 here. So this is the open loop gain, as well as this is the closed loop gain of the non-inverting operational amplifier. It is the open loop, it is the closed loop. And next, to interpret why op-amp is called as operational amplifier. So this op-amp, along with the amplification, it is also performing some mathematical operations like addition, subtraction, integration, differentiation, and logarithmic operations. So that's why it is called as operational amplifier, as it is performing the operations. And next, illustrate the magnitude of closed loop voltage gain of an inverting amplifier. So to find the closed loop gain of the inverting amplifier, I am taking the inverting amplifier. The non-inverting terminal of this one I am grounding. For the inverting terminal, we are providing the input voltage through the resistance, and the feedback resistance RF, we are utilizing the output voltage. So here the closed loop gain, to find the closed loop gain of this one, the output voltage is closed loop gain times the input voltage. So this value, if we calculate, we will get it as 1 plus RF by R1 here. So closed loop gain is equal to 1 plus RF by R1. So this value we have already derived in the previous slides. We already discussed in the OPAMPS sessions. And interpret the magnitude of open loop voltage gain of an inverting amplifier. So for the purpose, again I am taking the input I am applying to the inverting terminal of the operational amplifier, and the non-inverting terminal I am making it as the ground, and this is the output voltage I am taking. So the output voltage is open loop gain times the input voltage. So the open loop gain equal to V0 by Vi. So this is the value of open loop gain in the case of operational amplifier inverting mode. So in this session, we have discussed the different questions related to the operational amplifier circuits. Thank you.
Like, share and subscribe. Hit the bell icon for more updates.